Hello and welcome to this video that's reviewing the displacement reactions of halogens. Quite often when you do this in the laboratory, the nuance and the observations of what you see are sometimes lost. So I thought I'd do a little clip with some actual video footage of when I did it myself, and then talk about what's happening as it goes. At the end of the clip we'll do a long answer exam question, and I'll take you through it. And then hopefully that will help reinforce some of the learning you've done in class, as well as go with your independent study notes that you've done. So if you can have them to hand, that would be very helpful. So if we take a basic sort of displacement reaction and have our two halogens as X and Y. So the trends on the right hand side show you the comparison between the two atoms. In terms of reactivity, X will be more reactive than Y. In terms of oxidizing ability, X will be better at removing electrons than Y, because it will have greater nuclear attraction because it has less shielding than Y. On the other hand, in terms of reducing ability, Y will be better at losing electrons, so it's good at reducing other things, enabling them to gain electrons. So because Y has more shielding than X, there's less nuclear attraction in Y for the incoming electrons, so the outer shell electrons that it would lose are going to be lost more easily. So along the bottom are the things you need to be able to do. For the specification, you need to put down your observations as you see them. You need to be able to use oxidation numbers to prove that redox has happened, and you need to be able to use that idea to construct redox half equations. So let's start by having a look at adding chlorine water to solutions of bromide and iodide ions. While the clip is playing, because it's being performed in the fume hood, the noise from the fume hood is in the background, so I won't be talking over it, but I will be annotating it as we go. So let's now look at the observations. So when chlorine is added to bromide ions, the solution turns from colourless to a brown-orange colour. In terms of using oxidation numbers to prove redox, the best thing to do is to start by writing an ionic equation for what's happened, and then you can assign the oxidation numbers and see what the changes are. So start by looking at all the uncombined elements and assign oxidation number 0 to them. That's the easiest place to begin. Then you look at the ions. Now it's worth remembering that every ion that's made of only one type of atom is only going to be the same oxidation number as the charge. So therefore, if it's a negative ion, negative 1 ion, it'll be -1 oxidation number, for example. So bromide and chloride in this case are -1. So once you've worked that out, you can then draw a little arrow from one species to its equivalent on the right hand side, like that. Now what you do is you work out the change in oxidation number. So looking at chlorine first of all, it's going from 0 to -1, and bromide's going from -1 to 0. So if it increases in oxidation number, it's an oxidation. If it goes down in oxidation number, it's a reduction. So that means that chlorine is undergoing reduction and bromide is undergoing oxidation. So what we can now do is write a redox half equation to represent each half of that complete reaction, the reduction half and the oxidation half. So this allows us to say that chlorine is an oxidizing agent because it is removing electrons from bromide ions. So the reducing agent is the bromide ions because they are providing the electrons that are gained by chlorine when chlorine is being reduced. So this time, pause the clip and see if you can predict the observations. See if you can use the oxidation numbers to prove redox has happened by writing an ionic equation, just like we did in the previous example, and write the half equations like we did before. And see if you can add some conclusions of your own. So stop the clip, take a couple of minutes to do that, and then see if we're in agreement. So first, looking at adding bromine water to chloride ions, the solution turns from colourless to orange as the bromine is added, but there's no reaction because bromine is less reactive than chlorine, so bromide or bromine, either of them, are weaker oxidizing agents than chlorine, so they cannot remove electrons from Cl2. So when we think about the observations as well, it's worth noting that if you look at the colour of the iodide test tube, we now have a slightly darker solution in the test tube compared to the orange colour of the bromine in the bottle. So we can't just simply claim that the orange colour or darker colour is due to the bromine being added and swirling around with the iodide ions without reacting. So the fact that it's slightly darker must mean that there's something actually happening chemically. So the first thing to do is to construct the ionic equation and assign the oxidation numbers before we decide what's been oxidized and what's been reduced. Once we've done that, we can put in the redox half equations and we can conclude that bromine is reduced from 0 in Br2 to -1 in Br-. This is a decrease in oxidation numbers, so it's a reduction. We can also conclude that bromine didn't react with chloride ions, because Br is a less reactive element and a less effective oxidizing agent than chlorine or chloride. But we can say that bromine will react with iodide because Br is a more effective oxidizing agent or a more reactive element than iodine molecules or iodide ions. We can also see that iodide ions are oxidized from -1 in I- to 0 in I2. So this time it's an increase in oxidation number, so therefore it's an oxidation. So now what we can do is have a look at what happens when you dissolve the different types of halogens and halides. So I'm going to play you a short clip now of when I dissolved halogen molecules in cyclohexane. And this illustrates quite graphically the fact that halogen molecules only undergo London forces because they're non-polar. This is due to the equal electronegativity between the two halogen atoms. So halogens will dissolve much better in polar solvents such as cyclohexane, things like that, but halide ions are charged, so as a result they'll attract much better to polar solvents such as water. So if we take a chlorine molecule, halogen molecule, this could equally apply to bromine or iodine or fluorine. Each atom has identical electronegativity to the other, so no permanent dipoles can be set up. However, if you put a halogen into a non-polar solvent, what will happen is the London forces that are set up automatically in the halogen and in the non-polar solvent will cause the halogen to dissolve in the non-polar solvent. So what I'll do now is show you a little clip that shows this in action, so you can see it quite graphically yourself. So the thing to watch out for is the top layer. So I'll mix an aqueous solution of a halogen with cyclohexane, and if you look out for the change in colour of the organic layer on top, cyclohexane is colourless by itself, but it's less dense than water, so it'll float on top, and what will happen is the halogen will dissolve much more effectively into the organic layer. So you can see quite clearly the change in colour of the cyclohexane layer as the halogen dissolves in it. So this is a good way of showing not only the solubility in polar solvents, or non-polar solvents I should say, but this can also be used for the displacement reaction we looked at before. So this is a levelled response question. This is the more up-to-date type of long answer question you'll come across. And you can see that it's a levelled response question because you've got a little asterisk up by the word describe. So the thing to do now is to plan, but make sure your plan includes relevant subheadings, but a very simple idea of what to write for each one. So if you look at the question, it says, explain the relative reactivity of the halogens chlorine, bromine and iodine. So you can split your answer into 3 sections. So chlorine will react with both bromide and iodide, but it's the most effective oxidizing agent out of all of them. And bromine, finally, will react with iodide, but not chloride. So I'm going to physically cross out my plan, just to tell the examiner that I want their attention on what I'm writing here. So, when it says reactions with halide, what it means is the reaction of that halogen, or not, if it, as the case may be, with all the other halides. So you need chlorine plus bromide and iodide, just like we demonstrated. So you can start by doing the equation for chlorine reacting with bromine. So you can write the 2 equations, making sure you've got state symbols, and put the observations under each species, so it explains what the observations mean. And you can explain the whole thing by saying chlorine is a better oxidizing agent than bromine or iodine. You can write it bromide or iodide if you wish, but it makes the same point. So similarly, you can explain the reaction of bromine in this context. It's only going to react with iodide. So the trend is that the oxidizing ability is with chlorine being the most strong oxidizing agent, then bromine, then iodine. So in terms of iodine, it won't react with any other halogens, but in terms of the halide reducing ability, it's a different story. I- is a much better reducing agent than either bromide or chloride. So this takes us to the end of this clip. On my channel, this particular question is treated separately in slightly more detail if you want to have a look at it. It's in the playlist, I think it's on levelled questions.